starts. There you are. The stage is yours.
Thanks for the introduction and the invitation. And hi everyone, my name is Zhang, and I'm working as a postdoc in this observatory. And it's a great pleasure for me today to talk about my research on the first interstellar visitor, Oumuamua. As you may know, this object has a quite unusual shape and trajectory, and its appearance challenges many previous assumptions about how the small body from another planetary system may look like. So in this seminar, I would like to reveal its characteristics and present our explanations for its origin. So first, before we dig into the Oumuamua, I would like to give some general context about small bodies and their evolution. It's believed that in our galaxy, forming stars are usually accompanied by the protoplanetary disk. So planets will eventually form from these disks, and various kinds of small bodies also survive as remnants of this area. So this small body will have a huge diversity in terms of their formation and evolution. And the information content in this small body could help us to reveal the entire history of a system. So in recent years, more and more spacecraft are sent to visit some small bodies in our solar system, as summarized in these images. And these small bodies are shown with actual size scales. Unlike the planets and dwarf planets, the gravity of small body is not enough to squeeze them into spheres. So every small body, as shown here, will have its own unique shape and surface morphology, which corresponds to its lifetime story. So we can see that none of these small bodies looks the same, but there are some similarities, such as the trans-Newton object, oracles, and some comments like Churi have some kind of contact binary like biolobe shapes. And some asteroids like Itokawa and Tuitadis and Eros, and they have sort of elongated shapes. There are also some other asteroids have nearly spherical shapes with some equatorial verge, like Bennu and the Ryugu, which were explored by Observatoire and Hayabusa 2 mission recently. And this kind of shape is often called the top shape, as it's similar to the toy top. There are dozens of asteroids have this kind of shape, and some of them have like a small satellite, like the Didymos binary system, which will be visited by the Hera mission soon. So the question is how these small bodies get their current shape. And one possibility is that they were born just like this in the early stage of solar system. But for many asteroids and comets, the dynamical and collisional environments is very chaotic and active. So generally, their current shape are formed through various process of collisional evolution. So which will induce this body to be a reaccumulation aggregate after the collision. So as shown here, they have quite very low tensile strength. They're just like a robopite holding together by their own mutual gravity. So in this case, because this structure is so weak, their shape could also be modified by other effects. One important mechanism is the so-called Yog Effect. This effect can double the spin rate of a small body within like millions of years, and which could be shorter than their collisional lifetimes. In addition, the dynamical evolution of small body can sometimes like have some very close approach to a planet or star, and their shape can be largely modified or even be disrupted during the close encounter, like what happened for the Shoemaker Living 9. So these three effects are responsible for the shape changes evolve complicated dynamical process. So in order to decipher the small bodies' history from their current morphologies and shape, we need to explicitly model this process. So my collaborators and I have dedicated to developing and incorporating like several numerical tools to study this process for years. And we have revealed some features of this process. Like for example, in a study dedicated for the formation of Churi's shape, we found that the conditional evolution can generate a kind of biolob shape without delete the volatiles. And in fact, we have done sort of different simulations to involve the collisional disruptions and reaccumulation. And we found that diverse shape can be generated from the collisional evolution. And the rotational reshaping will tend to form the top shape as these surface particles, they will fail and induce some landslides when the spin period exceeds the robopite spin limit. And also for some certain internal structure and particle size distribution, this effect could also form some like pancake shape. And if the robopite has some kind of material strength, a biolob shape can also form through the Yog spin-up process. Unlike these other two processes, which can generate so different kind of shape, the tidal distortion and disruption usually will lead to elongated coalesced shape, like the movie shown here. These are all generated from our simulation. So ultimately, our understanding is that the shape evolution of a small body depends on its physical and chemical properties, and also its orbits related to the planets, the sun, and other small bodies. This figure shows a schematic view of the solar system, and we have small bodies that are distributed in a very large range of semi-major axes. The small body in the inner solar system are dominated by rocky and mantle materials, which are called asteroids. And in the outer region, small bodies could contain large amounts of volatiles. So when they are scattered into the inner solar system, they will become active due to the heating of the sun. And the orbital dynamics of small body is in fact quite chaotic. Like objects in the out cloud that are far away from the sun can be kicked into the inner regions of the solar system as the form of the long period comments. And similarly, perturbations of giant planets can also eject their surrounding objects into the out cloud or even interstellar space. And in fact, several solar system formation models have suggested that the orbital migration of the giant planets have ejected a large fraction of the original planetesimals into interstellar space. So it's likely that other planetary systems will also do the same trick. So there is a big hope of finding objects that have been lost by other planet systems in our own system. So there is a post. I need to go to there when I need to escape from the share screen to go to that. But I think I will reveal that after the talk. But feel free to choose your answer for like, what do you think, which kind is the dominating population for the interstellar objects? So let's continue. So finally, the dream of to seeking the interstellar objects come true 3 years ago. The first interstellar object, Oumuamua, was discovered on October 19, 2017 by the Pan-STAR telescope system. At the time of discovery, it has passed its perihelion to the Sun. The perihelion distance of its orbit is about 0.25 astronomical unit, and its orbital eccentricity is about 1.2, which identifies it to be an interstellar object. The image here shows its point-like appearance without any detectable cometary activities, which means it's kind of asteroid-like body rather than a comet. And since the discovery, more and more observers joined the observational campaigns and confirmed that Oumuamua exhibits no evidence for the cometary activities and support its identification to be an asteroid. And the photometric and spectral characterization by its surface is kind of red and could be like organic rich or iron rich and may subject to some space weathering effect. And its color is in fact similar to many solar system small bodies, such as some comets, some Jupiter children, and some non-period comets. And so also its brightness range was unusually large. Its light curve shape has a narrow V-shaped minimum and a broad maximum, which indicates that these large brightness variations are caused by its shape and rotation, not the variation in its surface albedo. So according to the light curve, the ratios of the shortest axis to the longest axis was inferred to be smaller than like 1 to 6. Since we don't have the orientation of its rotational pole, this X ratio represents only like an upper limit. And the average brightness indicates its size is about 100 meters. And it's also evidence that the light curve doesn't repeat exactly from one night to another. So this indicates that Oumuamua is a tumbling rotator. Its light curve frequency is close to a span period of 8 hours. And another notable thing is that its heliocentric incoming velocity. This velocity is remarkably close to the mean motion of the stars in the solar neighborhood. So it has a very small deviation from the mean velocities in these two, the U and W directions. And since younger stars has smaller velocity dispersion than older systems, so this small deviation would suggest that Oumuamua may come from a young stellar system. Well, for the second interstellar object, Paris-PSL, which is discovered in 2019, its speed variation is much larger, suggests that it comes from an older system. And another big puzzle is that although it has been identified to be an asteroid, Oumuamua's trajectory showed a non-Keplerian feature. Combining all the available observations, a detailed investigation of its astrometric position measurements showed that a gravity-only orbit is inadequate to fit the data. And a radial acceleration in a form like this is required to explain its orbit. This type of acceleration is usually interpreted as a result of cometary activities, but this is contrary to its point-like behavior. So overall, these observed features of Oumuamua raise many puzzles. Let's find out. So first, although orbital migration of giant planets can eject small bodies into interstellar space, rocky bodies are actually much less likely to be ejected than icy bodies because the planets are more massive and the escape speeds are lower outside the snow line. And also because of the sublimation of a comet can make a cometary body more visible than an asteroid-like body with the same mass. So since the first detected interstellar object is kind of like asteroids, not comet, the fraction of cometary bodies in the interstellar space may be very small. And the detection of Oumuamua inferred a large population for the rocky interstellar object. It's difficult to supply the required number density. And also, since its velocity relative to the LSR indicates it comes from a young stellar system, which will make the number density budget much worse. And its invert, the shape is very kind of unique. None of the small body in the solar system can have such an extreme shape. In this picture, this blue point shows the shape distribution of solar system small body. And I would like to also point out that the light curve variation could also not only just indicate an elongated body, it may also can be consistent with the light curve of extremely oblate shape. But how to form these two kinds of shape and maintain their stability and tumbling state is a very challenging question. And also, among all the possible sources to account for the non-gravitational acceleration, the solar radiation pressure will require a very low bulk density, while the outgassing is contrary to the absence of coma. So all these puddles are very hard to be solved in a consistent way. And the fact that the secondary interstellar object solved fits the previous assumption about the interstellar objects will make Oumuamua even weird. So that's why some artificial alien spaceship idea is invoked when we try to understand the Oumuamua. And this figure is just for joking, but a few scientists actually advocated the idea that Oumuamua is an alien technology and have wrote a series of papers and published a book about this idea. They suggested solar stealth is the reason causing the observed non-gravitational acceleration. But there is no compelling evidence to favor an alien explanation for Oumuamua from current evidence. Actually, scientists use this alien telescope area to search for radio transmissions, which could help to indicate a non-natural origin for this object. And they actually found no evidence of artificial transmitters within the measurement ability. So in our study, we want to construct an evidence-based scenario to understand Oumuamua's origin. And this paper here, published in 2019, gives some strong arguments about why Oumuamua should have a natural origin, and revealed the conventional physical process that could explain Oumuamua's origin. But these formation models are still difficult to reproduce all its puddling characteristics. And among these models, the tidal disruption followed by ejection can generate asteroid-like interstellar objects from the inner planetary system. but it's not clear if this way can explain Oumuamua's shape and the non-gravitational acceleration. And there are also some other alternative natural explanation to account for the non-gravitational acceleration rather than the solar cell. So in support of the solar radiation pressure, some study have suggested that Oumuamua has a very low density due to a fractal aggregate structure. Such extremely low density object has never been detected, but may help us to understand some process in the protoplanetics and disrupting comets where these objects are suggested to be found. And it's also possible that the non-gravitational acceleration is caused by sublimation of undetected volatiles like hydrogen ions. But some other studies suggested that the hydrogen ions would be destroyed during the interstellar journey. Therefore, we would like to explore other possibilities to account for the non-gravitational acceleration. So please choose your idea. What's the origin for the Oumuamua? And so as we recalled from the slide in the beginning of this talk, based on our past research experience on the small body shape evolution, it seems more likely that an extremely elongated object could be generated by the tidal distortion and disruption process. So we would like to focus on this tidal disruption and formation scenario. The tidal disruption events are actually very common in planetary and stellar systems. Oumuamua's reddish surface actually suggests that it may have come very close to its host star and experience some strong radiation. Therefore, to resemble its surface feature, we consider that its parent body may experience a close encounter with its original host star. Just like in the solar system, some long period comets, which also called sun grazing comets, they will pass extremely close to the sun as a perihelion, as shown in this region. And in some cases, this encounter could induce a tidal disruption event. So our formation scenario begins with the assumption that Oumuamua originates from tidal disruptions by the host star of its home planetary system. We use our high-efficiency empirical field graph to simulate the tidal close encounter process. And based on the knowledge of small bodies in our solar system, the properties of Oumuamua is assumed to model in a way like this. The simulated parent body with assumed to be a rubble height and with a radius of 100 meters and a bulk density like this. And the host star is assumed to be a main sequence star whose mass is like half of the solar mass. And we choose the encounter condition to meet the tidal disruption requirement and the ejection criterion. So the perihelion distance need to be smaller than the tidal disruption distance, which depends on the body's material cohesive strength and the friction angle. And the ejection criterion require an eccentricity close to 1. And this criterion is size dependent. So for a parent body like this, the initial orbit to eject fragments should like this. And this movie shows the tidal disruption process we generate from our simulations. So we can see that as approaching the star, the parent body is spun up and then really distorted. and then it will be disrupted by the tidal force. And many fragments are produced during this process, and some fragments can escape from the host star and become interstellar objects, as indicated by their colors, just this red one. And we analyze the spin period and the shape distribution of the resulting fragments, as shown in this figure. We can see that many elongated coalesced fragments can be produced from the tidal disruption process. The typical X-ray ratio is about 0.2 to 0.3. The symbol size represents the size for each fragment. They are quite close to the size of Oumuamua. And the color of each symbol represents the rotation state. If the rotation index is not equal to 1, 0, or -1, the fragment is rotating in a tumbling state. So as shown in this picture, most of the fragments are actually tumbling rotators. We can compare with the result with different friction angle. We can see that a higher friction angle can generally produce more elongated fragments. And the fragments with axis ratio smaller than 0.3 can be produced even with a material friction angle as low as 27. So this implies that the production of extremely elongated fragments through the tidal disruption process is very common and efficiency. And here are some examples of the elongated fragments formed by tidal disruption in our simulation. So, but given that our previous analysis shows the shape of Oumuamua has an X ratio close to 0.1. So we cannot achieve that kind of shape by just increase the friction angle. We need to consider the material strength, like the cohesion. So we conduct the thermal modeling for the closed stellar flyby. And the thermal modeling show that the surface material of the parent body exposed to the star, they will melt near perihelion and then concrete 3 hours later after the perihelion. Here, these solely curves with different colors show the temperature devolution of the parent body at different depths. So such thermal process may induce the formation of the sintering bonds between surface particles and adding cohesive strength into the material. So in this case, these particles have a higher resistance to their relative motion. So we use the simulations to explore this possibility. We perform this kind of simulation. The parent body is cohesionless in the beginning, and some cohesion is added into its material 3 hours later after perihelion. So as shown in this movie and also these figures here, we can see that extremely elongated fragments with X ratio close to 0.1 can be formed through this later turn-on cohesion process. And here is an example of an extremely elongated object that is formed by this such process. So this will provide a reasonable formation mechanisms for the shape of Oumuamua.
Sorry to interrupt you, Jan, but just can you just show the previous? Here you're showing all the fragments, or just the ones who escape the gravity of the star?
Yeah, this figure shows all the fragments.
Okay, so the ones that escape the gravity, where are they? They are located.
They are usually located in the far side of the fragment.
But they also can have the same characteristic like C over A 0.1 if they escape, or?
Yeah, they have a very similar characteristic.
Okay.
Yeah.
Sorry.
Yeah, and in our study, we did not involve the later, we did not consider the effect of planets.
Okay.
So,
but even here already they can escape. They can get a kick in velocity that is enough for them to leave the system.
Yeah.
Okay.
They can escape the gravity of the star.
Okay, thank you.
Thank you. So let's continue. So now we consider when these fragments leave their star, what's the process act on them. So like after they has been ejected from their host stars, these fragments' motion is gravitationally accelerated and dragged by the interstellar gas. And also their motion could also be like affected by the interstellar magnetic field through the affluent propulsion. So as the Oumuamua moves through this magnetic field, an electric field is induced across it, and this will cause the kinetic energy dissipation. So in this case, when a dynamical equilibrium is established, the interstellar object will attain a size-dependent terminal speed relative to the local standard of rest. For a Oumuamua-like size object, like from a few giga-years ago, the terminal speed is about 10 kilometers per second, which is consistent with the observational speed for Oumuamua. So Oumuamua is not necessarily come from a young stellar system. But this magnetic effect is less effective and has longer time scales for larger interstellar objects. So like the second interstellar object, Brosov, has a larger speed relative to the local standard of rest. And next, we need to check if the ejected fragments can have a surface similar to Oumuamua. And as this figure has been shown before, just thermal modeling have shown that the heat diffusion during the tidal close encounter process will consume a significant amount of volatiles. So these dashed lines indicate the sublimation temperature for these volatiles. So as indicated by this red light, at 3 meters beneath the surface, the temperature can reach like 28 Kelvin. So such that a large fraction of low sublimation temperature volatiles such as CO can be depleted. And given if we consider Oumuamua is elongated size with like 100 times 10 meter object, this duplicity will just process into its whole body. And in fact, these depletions provide an explanation not only for the Oumuamua's spectroscopic properties and non-cometary activities, but also for the infrared giantness of the whole interstellar population. So we could have many more asteroid-like interstellar objects than we previously thought. However, since the subsurface region is less heated by the star, higher sublimation temperature volatiles like the water ice and CO2 buried on the surface are still condensed. If Oumuamua is one of the fragments that originated from the parent body's interior, so in this case, most of its surface area would be exposed to the star only after the tidal disruption. So in that case, less heat will be transferred to its interior, and more volatiles can be preserved at a shallower depth. So now we want to find the explanation for the Oumuamua's non-gravitational acceleration. Since there are some preserved volatiles, so when it comes to visit our solar system, its surface could be once again exposed by the sun's intense radiation, and the residual volatiles could be activated. And the observation on Oumuamua has put some upper limits on its gas production rate, as shown in this table. So if the non-gravitational acceleration is provided by the outgassing mechanism, the required production rate is like 10 to the 25 molecules per second. So according to this table, only the water ice is a viable source for outgassing that may potentially account for the non-gravitational acceleration. So this figure here, we simulated the heat conduction process for Oumuamua during its solar system passage. And the depth of the evolution of the water and CO2 sublimation layers during Oumuamua's flyby in our solar system is shown by these two solid curves. The red and green dash and the dotted line represents the buried depths of the residual water and CO2 ice in the formation process, showing these two figures. And the observation spans of the of Oumuamua is indicated by this light blue region. We can see that plenty of residual waters and CO2 ice can commence sublimation during the observational span. But since the CO2 is buried deeper, its sublimation may be delayed and cannot be observed during this observation span. So if we account for the total amount of water sublimation to explain the non-gravitational acceleration, we will require amount like this, which is smaller than 1% of the Oumuamua's assumed mass. So in this way, the water is sufficient to account for its non-gravitational acceleration. So now let's go back to the puddles of Oumuamua and see if our simulation result and the proposed scenario can explain its puddles. So as shown in previous slides, the puddle regarding the shape and tumbling rotation and no cometary activities and velocities can be well solved. And also some residual volatiles that can commence sublimation and provide the source of outgassing to account for the non-gravitational acceleration. The last question we need to answer is that if this formation scenario can produce the required number density for an Oumuamua-like interstellar object. So to estimate the mass budget of Oumuamua-like interstellar objects, we need to consider the properties and populations of both the host star and the parent body. The most possible host star is the low mass sequence star. So first, since the radius of main sequence star is proportional to their mass, and the tidal disruption distance is proportional to their mass, the star's mass with a power of 1/3. The low mass stars have a higher density and a larger region that allows tidal disruption to occur. In addition, the low mass stars are more numerous and generally have more planets. So these two pictures can make a large contribution to the Oumuamua-like interstellar object population by tidal disruption. And also, as the post-main sequence byproduct of stars, white dwarf may retain some residual icy planetesimals and planets. And since they have very high density, the tidal disruption process is very active and efficient around the white dwarf. However, the population of their progenitor is not as large as the low mass main sequence star. So white dwarf may contribute a small fraction to the original host of the Oumuamua-like object. And what's the possible parent bodies? We, based on the described formation and the ejection mechanism, the long period comets on nearly parabolic orbit are the most promising candidates for the Oumuamua's parent bodies. Under the combined influence of the galactic passing start and the planetary perturbation, a few kilometer-sized long period comets will come into the star's proximities every year. And this figure here shows such an orbital evolution of an out cloud object evolved into a observable long period comet. And the mass budget of long period comets per star is estimated to be much larger than the required mass ejection of Oumuamua. So this long period comet can provide a sufficient supply for the Oumuamua-like interstellar objects. And the diabretics around in some systems are also potential parent bodies. So therefore, the number density of interstellar objects produced by the tidal disruption scenario can well account for the detection of Oumuamua. So in effect, our result offered a viable solution based on all this evidence. The alien spaceship proposition is not necessarily required. So here is our final pause. Please write down your answer. So, moreover, in our attempt to address the plausible cause for the Oumuamua's features, we also highlight the high efficiencies of producing the interstellar object, and highlights the large population of the asteroidal interstellar object. And also although these objects may be not related to intelligent creatures, it's possible that they contain some life building blocks like the water and organisms, and spread these materials in the whole galaxy. And our explanation is provides a viable hypothesis, but we cannot verify this from Oumuamua anymore, as it has been too far away from the Earth. But future observations, especially with the development of the Vera Rubin Observatory and the space missions like ESA's Common Interceptor mission, will help us to detect more interstellar objects and have more information about them. So if the proposed scenario works, we will see more Oumuamua-like objects in the future, which will help us to answer the 3 questions I listed in the poll. So in summary, I shown that the small body are commonly reshaped by 3 different major processes, and we developed several numerical tools to model this process and identify the general shape features of small bodies and the relation to their possible origin. And with the application to Oumuamua, we found that the Oumuamua's attributes can be produced naturally while tidal disruption evolution. And with the analysis of its host and parent body, we found that it's possibly generated from a planetary system with a low mass host star. And due to this Oumuamua like interstellar object need to experience a tidal downsizing process, they will tend to be smaller than cometary interstellar objects like Sol. And also due to this, their small size, they usually will have a smaller local standard of rest speed. And in our final remark, we would like to remind that the life proliferation around this galaxy is also possible by these interstellar bodies. So thank you very much.
Thank you, Yoon. Maybe we should have a look at the polls results now to see what people voted for. So you're still sharing your screen, so maybe you can go to the Q&A tab yourself, and I'm going to display the results. Right.
Yeah. You want to share your screen?
Yeah, I can do that if you want, yeah.
Okay.
So just bear with me a second. Share screen up. Right, can you all see my screen?
Yeah.
Yeah, perfect. So these are the results. So if you want to comment on the correct answer for the first one.
Yeah, that's actually for these three questions, we do not have absolutely right answer. So
okay,
all these can be true.
So people were almost right.
Yeah, so everyone.
For this one as well. Yeah. And oh, this one's got a strong, favor for number one.
Yeah, I'm glad that the natural origin convinces all of you. And it's I would like to say we cannot 100% rule out the possibility of an alien probe, but we don't have any evidence for that. So it's a scenario cannot be proved or not. So that's not the science we want to do. So in our case, we will be in favor of the natural object. And in fact, as I mentioned in the end of the presentation, with more and more information and discoveries about future interstellar objects, we can finally know if the Oumuamua is actually a natural object. In this case, we can maybe with more confidence to rule out its artificial origin. And also we will know more about if it's statistically proportion between the asteroid interstellar object and the cometary interstellar object.
Okay, thank you. So we still have about like 10 minutes if people have questions for Yoon.
I have a question.
Yeah.
Maybe you said it, but maybe I missed it. The scenario you explore for the tidal disruption is around a low mass star. Why do you need a low mass star? Why couldn't it work with a solar type star, for instance? What is specific to the low mass star case that makes the tidal disruption more like what we want?
Yeah. That is a key question to validate our scenario. Just because our scenario involves the tidal disruption, when the object comes very close to the star, in order to involve the tidal disruption, it needs to come very close to the star. And in this case, like for our sun, the tidal disruption distance is for most small body is already smaller than the sun's radius. So
Okay.
they will not be disrupted before they enter the
Okay,
sun.
okay. It's, yeah, you have to take into account the size of the star. Okay. And that's maybe why we don't see anything having this shape when we look at small bodies in the solar system, right? Because nobody comes close enough for this to happen.
Yeah.
Okay.
Here in one case, the common ozone, it comes very close to the star and then been distributed. So
Okay.
we don't have that kind of things happening in our solar system yet.
Okay, thank you.
So I see that Sylvie is raising her hand. So yeah, Sylvie, go ahead.
Hi, thank you very much for this talk. I am not at all an expert in this topic, but you made it really clear for me. I work on young stars, so it was interesting to hear that this has to come from a relatively young system. I was wondering, so I understand that outgassing is possible because there is no upper limit on the water ice, on the H2O, on water vapor outgassing from the data that were taken. I was wondering, what is your limit on the bulk density of the primary object that was tidally disrupted? Did it have to be a rubber pile type, or could it be a comet type object? Or, I mean, you must have a constraint on that.
Yeah, we in order to be tidally disrupted, it has to have a low strength. So it works for both rubble pile or common like. Actually, like for the Zeta mission's target 60 Curie, it has a very low tensile strength.
Mm-hmm.
And in this case, the common like object can be also be disrupted.
Okay, so an object like a comet, a typical comet nucleus, could be a good parent body. Okay, thank you.
Thank you for the question.
So I see we have a question in the chat as well from Nicolas Biver that needs to head off now. So that's why he's asking the question in the chat. So the question is, what's the largest size possible for a monolithic object created in a collision of any shape, like a big boulder on Itokawa?
Yeah, I must say we don't have a very specific answer for that yet. And according to the space missions, the images returned from the Bennu and the Ryugu, we found that the big boulder could be as large as like 100 meters in diameter. And this will be generated by a catastrophic impact and survive from that process. And with and according to the analysis of the asteroids span and size relation, we found that for asteroids that are larger than 200 meters, their span rate is usually smaller. Its span period is usually larger than 2 hours, which means they will be held by a rubble. They will be a rubble pile held by gravity, so they cannot speed faster than the 2 hours. In this case, we will usually put the largest monolithic object size to around 100 to 200.
Okay. I don't see any other hands raised. Like, do we have any more questions for you?
I have a question.
Yeah.
Yes, in the paper, we see that based on the upper limit on the production rate of the various molecules which were observed, the outgassing causing this non-gravitational acceleration is excluded. And you seems to not agree with that. So what is new in your approach?
Which paper you Could you suggest that which paper is that?
No, but I don't know exactly which one, but this is part of the mystery of this object, is that there is a non-gravitational acceleration and a low outgassing. And
yeah, as I showed in the table, there is a upper limit on the observable volatiles.
yeah,
And
so you are arguing that the upper limit that we have on water is high, so we cannot exclude.
yeah.
But there is also the dust. We don't see any dust. So this means that the outgassing of water should be quite low also, because we don't see any dust.
Yeah, the dust, if I remember correctly, the size, we did not observe any micrometer size dust, but the observation cannot rule out the existence of dust above like 0.1 millimeter. And so we cannot completely rule out the existence of the dust. And if it's generated by the tidal close encounter with the stellar, some micro-size dust may be melted. So, but we did not explore that specifically.
Okay.
Yeah, that's a good thing to think about. Thank you.
Okay, thank you.
Yeah, Bruno has a question as well. Go ahead, Bruno.
Okay, hello. Oops. Can you hear me?
Yeah.
Okay. So my question is, maybe I missed it, but have we some constraints on the shape of Borisov?
There is not research, as I know, that about the shape of Borisov, because it's a comment and its activity is kind of strong. And at the end of this travel, is kind of disrupted by the solar heat. So we do not have the detailed information about its shape.
But is it extremely elongated or not?
Oh, it's not extremely elongated. It's quite common. It's just a common comet.
Okay.
Yeah, it's very like someone we have observed in our system previously.
Okay, thank you.
Thank you.
Est-ce que moi c'est juste, sorry, it's just to pursue on Dominique's question, and I see that also Louis Dandecourt had a similar question about this sublimation. Just to make sure I understand, there was no direct observation of the water. I mean, in the table that you showed, there was upper limit on OH, but not on water vapor.
Yes, but the OH is water. OH is
Yes.
you have direct access to the
Yes.
to waters
Yes.
from OH.
Okay, so
Yeah,
that's what I inferred. And so what Yun Zhang is telling us is that the required sublimation rate of water that you need is compatible with the upper limit on the OH gassing. Okay. So the real problem is the dust. It's just the dust. The fact that there is no visible coma.
except if the dust is made of very big
Made of
particles.
large particles like she said.
Yes. Yeah.
Yes, which we cannot exclude because of the tidal processing. Okay, just to make sure I got that. Thank you.
Thank you.
Are there any more questions, or are we done? Right, if we're done, then I'm going to thank everyone for coming to this talk. I'm going in particular to thank Yun for giving this very nice talk to us. And we'll see each other next time for the next Séminaire. All right, Bye-bye, everyone.
Thank you very much.
Very good.
Excellent.
It's a big pleasure for me. Thank you.